Hello students, now we are going to review the Dijkstra's algorithm. Let me go over the relaxation principle behind the algorithm first. So every iteration will basically try to find the shortest path from the source vertex to a particular vertex. So that vertex U is the vertex that has a minimum weight among the vertices that are yet to be optimized, which means the vertices for which you're yet to find the shortest path. So if you have a vertex, say U, that is among the minimum, then it means you have found the shortest path. So then we try to explore the neighbors and see if you can reduce the weight of the estimate of the path to those neighbors. So let's say there's an edge U to V, and you want to see by going through U if you can reduce the weight of the path to V. So you're checking if the weight of the path from S to V, there is some path from S to V, and we have an estimate of that path from S to V, and by going through U, weight of the path from S to U plus the weight of the edge U comma V. So if this weight from S to V can be reduced further by going from S to U and then U to V, then we can set weight of the path from S to V is weight of the path from S to U plus weight of the edge U comma V, and the predecessor of V is going to be U. Okay, so as I said in class, for example, if this is say some 20, and if the weight of the edge is say some 10, and if this is say some 100, so 100 is going to be greater than 20 plus 10, 30, right? So then we can set the weight of this path from S to V to be 30 instead of 100 and make this edge to be the predecessor edge. Alright, so now let's go through an example. Anything, probably let's see this. Now we can go through this. Alright, so to start with, let's say this is the source vertex A, and we want to find the shortest path from A to every other vertex. So the source vertex can reach itself at cost 0, and the estimate of the weight of the shortest path to every other vertex is infinity. Alright, so now between among 0, infinity, infinity, all this infinity, the minimum is 0. So we pick A, that's the vertex with the shortest path from A to A. So now by going through A, we can see if we can minimize the weight of the path to the neighbors. So 0 plus 5 is 5 less than infinity. So we can set this 5 and make this as a predecessor edge. Similarly, 0 plus 3 is 3 less than infinity, so we can make this as the predecessor edge. So initially it would have been like this, blue. So between now 3, 5, infinity, 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 we have to pick the minimum weight. So that makes this F to be the vertex that is optimized. So now through F, we are going to see if we can reduce the weight of the path to reach its neighbors, which are B and E. So 3 plus 1 is 4 less than 5, so we can remove the highlight on this edge and make it this edge. Okay. Similarly, 3 plus 8 is 11 less than infinity, so we can make this as the predecessor edge. So now, so this would have been initially this blue. So now we have to pick the minimum weight among 4, 11, infinity, infinity. So we pick 4, so that makes this the optimized vertex now. So now we are trying to see by going through B whether we can minimize the weight of the path to reach its neighbors, which are D, E, and C. So now you see the weight of the path to reach E, if you go through B, would be 4 plus 2, 6, which is less than 11. So we can make it 6, remove the highlight on this edge, and highlight this edge as the predecessor edge. Similarly, 4 plus 2 is 6 less than infinity, so we can make it 6. So to start with, this would be blue, and 4 plus 6 is 10 less than infinity, so we can make this predecessor edge. So now between this, there's 6, 6, 10, we select the minimum weight. So there's a tie here now. So when there's a tie, I break it by alphabetical order, so I pick D instead of E, so I make this to be my optimized vertex. So now by going through D, you see whether you can improve the weight of the path to E. If you go through D, it would be 6 plus 5, 11, which is not less than 6, so we stay with whatever we know. But you see 6 plus 3 is 9 less than 10, so we can make it 9 and highlight this edge and remove the highlight on this edge. Okay, so this is the predecessor. So now this E is initially blue, but between 6 and 9 we can pick 6 as a minimum, so that makes this to become the optimized vertex. And but all its neighbors are already optimized, so that leaves with C, and C is also all its neighbors are optimized, so that's the thing. Okay, so if you put together all the dark edges, you get this shortest path tree starting from the source node A to every other vertex. Okay, now let's go through the analysis of the time complexity of the Dijkstra's algorithm. If you look at the pseudocode, so in an exam point of view, from exam point of view, I'll give you the pseudocode and you have to analyze the time complexity. So to start with, we set the weight of the path from the source to the source as 0, and the weight of the path to every other vertex as infinity, right? So to set V vertices, it will take that of V time. Now we have to construct a min heap. So a min heap stores the root with the lowest weight value. So we know the weight of all the vertices, so we can use the bottom-up approach to construct the min heap, and it takes that of V time to really construct what is called the priority queue, which is an implementation based on min heap. Now we extract the vertices from this priority queue one at a time. So to extract one vertex from the min heap or the root vertex, it takes state of log V time to rearrange the heap and restore the heap property. And we do this state of V times. For each iteration we extract the min weight vertex, right? So then this becomes V log V as a time complexity for removing the root from the heap and rearranging it overall. So then the relaxation step, basically when we looked at this example, any example it is true, we will go through every edge, right? So we explore the neighbors, right? And actually then we explore we explore each edge twice. Okay, so once from this vertex and once from this vertex, right? And again from A's point of view and B's point of view. So either way, we explore an edge 2E times, which is still theta of E. So whenever we explore an edge and we could change the weight of the node, for example, we reduce this from 5 to 4, so the position of B in the min heap changes or could change, right? So in the worst case, let's say it changes, then it takes again log V time to rearrange the heap. So if we traverse the edges totally that of E times, and each time we end up changing the vertex weight, it takes log V time to rearrange the heaps. So the time complexity to do the relaxation across all the iterations of the algorithm is theta of E log V. So the overall complexity is going to be theta of V plus theta of V plus theta of V log V plus E log V. So between these four, Of course, these two dominate this v, so we discard this. So v log v plus e log v. So between v log v and e log v, e term dominates because the number of edges is at least what, v minus 1, right, for a graph to be connected. So and e can be at most v squared. So that's why this term dominates. So the time complexity is going to be theta of e log v. Okay. Alright, let's now see some proofs. Now the subpath of a shortest path is also a shortest path. How? Let's say you are given a path S, A, B, C, D. That's the shortest path found by Dijkstra's algorithm. I want to show that A, B, C is also a shortest path. If A, B, C is not the shortest path, it is from the weight of the path from A to C is not the shortest by going through B. Let's say there is some other alternate path through which if you can go from A to C, shortest weight, then we can actually go from S to A and through that alternate path to C and then to D with the lower weight. So that makes S, A, B, C, D, this whole path itself to be not optimum. So it's a contradiction. So always a subpath of a shortest path is also a shortest path. Okay. Now let's prove the correctness of Dijkstra's algorithm. Let me see if I can use this. So we have a source vertex okay, so we have a source vertex S, and let's say we just optimized by finding a path to say U. Alright, so let's say that path be denoted okay, something like this, right? So alright, so let this path be some P and the weight be some D of U, okay, through path P. So now we want to prove the contradiction or assume first a contradiction that there is an alternate path P prime, okay, so which means you can go from S to U. Let me just use straight lines, okay, through some alternate path right, which is this P prime, okay, and the weight of this path going through P prime, D of U by going through P prime, is less than of the weight of the path P. Okay, now we want to see if this is really possible. Okay, now there are two situations here. There could be some intermediate vertices on this path or every in both these paths, right? So the situation is or all these intermediate vertices, say now we're looking at P prime, all these intermediate vertices that are part of P prime could be either optimized already, or there is at least one vertex in this path P prime that is yet to be optimized, means for which you are yet to find the shortest path. Okay, so let's consider the second case. Okay, so consider a vertex V in P prime. Actually, consider an intermediate vertex V in P prime for which we have not yet found the shortest path. Now, if that is the case, the weight of this vertex B would be the weight of this vertex V would be greater than or equal to U. Why? Because if you look at how Dijkstra's algorithm works, any example, the shortest path weights that you optimize every iteration keeps on increasing. Start with it as 0, then 3, then 4, then 6, another 6, then 9, right? So it keeps on increasing, stays the same or increasing, it never decreases. So which means if you picked U to be the vertex you want to optimize, which means the weight of V has to be at least the weight of U. Okay, so the weight of V has to be at least the weight of U, otherwise you would have picked V, right? So if that is the case, and given that Dijkstra's algorithm assumes all edge weights are positive, then it takes at least the cost of U, weight of U, to go from S to V. Then again you add some more edges, at least one more edge. Then the weight of the path from S to U by going through V should be more than the weight of the path that you have currently from S to U through P. So we rule out a situation where there is even one intermediate vertex for which we have not optimized. So that is ruled out. So which means all these intermediate vertices should be already optimized. Okay. So if that is the case, now let's consider a vertex V, which is over here, and let's consider a vertex U or W for which you have, say, the edge directly connected to U. So the same thing holds true for here. These two vertices, right? They should be already optimized. Alright. So when we optimize the vertex, what we do, we do a relaxation step, which means we try to see if we can reach the neighbors through a lower path, a lower weight path. So which means when we were relaxing the neighbors of W, we would have seen if using this edge we could reduce the weight of the path to from S to U. Similarly, when we are relaxing V, we would have checked whether we could reduce the weight of the path from S to U through V. So by going through all these things, we would have done all these things, right? So after going through all these things, we have a situation where we have picked path P, right? So which means the weight of this is the best predecessor, right? Because if we could have reduced the weight of the path to U by going through V, we could have chosen it, isn't it? So the fact that the Dijkstra's algorithm gave us this path means that this is the best predecessor through which you can reach U from S in terms of weight. Okay, so which means P prime, the weight of the path P prime from S to U, this path has to be greater than or equal to, it cannot be less than the weight of the path P from S to U. Okay, so this is the proof of the correctness of Dijkstra's algorithm.